Next up, we have to talk about concavity. Oh, there we go. All right, so concavity is not what you get in your teeth that you have to go to the dentist for. So we're not going to be drilling any teeth here, and that's my awful joke. I promise to make many, many more of them. All right, so what is concavity? Well, concavity describes the shape of the curve. Because right now, with just knowing increasing and decreasing, we just know the direction of the curve. Is it going up? Is it going down? But we don't know the shape. Now, there are 4 types of concavities, and hopefully you can count them in each of the different corners. I am 100% distracted by Caleb's cats. I'm not really sure what's going on right now. It definitely looks like a 1980s music video for a band called Cats. Kind of scaring me, creeping me out, but okay, cool. Got to focus, cool one. Back to math. All right, 4 types of concavity, 1 for each of these boxes. So there's really only 2 classifications for concavity. You can either be concave up or concave down. Those are the only 2 options for concavity. However, going down like kind of a sub-level, concave up has 2 versions and concave down has 2 versions. Concave up increasing, concave up decreasing. Concave down increasing, concave down increasing. So we're going to quickly draw pictures of what these are going to look like. All right, so I wouldn't draw the first picture, wait for the second picture. Watch my animation. So if we're increasing, we know that we're going to be going up, right? And if we're decreasing, we're going to be going down. However, that just, again, tells us the direction. What does this look like? Well, concave up means we're going to take the curve and we're going to pop it, and we're going to top it inwards. There we go. And with concave up decreasing, we're going to take the decreasing slope, but we're going to pop it inwards. So concave up pops the graph in. Now a concave down, again, we have our increasing and our decreasing directions. But with concave down, instead of popping in, we're going to pop out. So concave down increasing will pop out. And concave down decreasing will also pop out. So every single function that we are aware of in this entire world has these 4 different shapes somehow attached to it. Now, they might be manipulated, they might be stretched out vertically, they might be stretched out horizontally, things like that. But they are all functions are going to have these 4 shapes in them somewhere. All right, can I move on? So here's a graph. I just want to come through and identify the different concavities that we have. So here I just have different points, 0, A, B, C, D, E, and then x equals 8. All right, if we look from 0 to A, so for this chunk of graph right here, does this look like we're popping out or are we popping in? Out, in. I missed all 3 people in the chat. Yes, everybody says out. So I agree, it's out. And if we pop out, that means that this is concave down. And more specifically, it's concave down increasing. All right, then if we go from A to B. From A to B, what do we think? Are we popping in, or are we popping out? In, out, in, out, in, out. I'm getting an out again. And I agree, we're also popping out. So this is an example of a concave down. So we are still concave down, but this time we are concave down decreasing. All right, so then from B to C, what do we think? Are we popping in or are we popping out? I would agree. This time we are popping in the other direction. We are popping inwards. So this would be concave up, but specifically concave up decreasing. And then from C to D, we are also popping inwards. So this is concave up, more specifically, increasing. I think I left out a couple letters there, but that's cool. That's cool. And then from D to E, we are popping outwards. So concave down, but this is increasing. And then from E to 8, we're also popping out. So this is also concave down, but this time it is decreasing. All right, so hopefully we can see from the different colors, we have 3 intervals of concavity. 2 of those intervals are concave down. 1 of them is concave up. Oh, sorry, I thought I hit the mute button, but I didn't. All right.
Bless you.
Thank you. Can I move on? All right, so how do we actually find concavity? So fortunately, there is a test for concavity. And as you're copying this down, hopefully you notice the test deals with the second derivative, which is why we went over finding the second derivative in Unit 2. And I'll give folks a moment to copy this down before I start explaining and moving on and yada, yada, yada. Guys, not copying down yet? I'm a little bored. And since I'm a teacher, I'm the only feelings that matter. And let's see, Barbara says, Charlie Brown. Yes. I assume we were referring to my virtual background for this week. This is from Charlie, the Great Pumpkin Charlie Brown, the Halloween-themed Peanuts cartoon, which I assume will be on TV at some point. Or if you have the fancy Apple Plus TV service, apparently you can watch it on there too. All right, but okay, a test for concavity. So increasing and decreasing is the first derivative. Concavity is the second derivative. And we follow the same process as we do with increasing and decreasing. We find the second derivative. If the second derivative is positive, it's concave up. If the second derivative is negative, it is concave down. Now, in order to help us remember concave up versus concave down, positive second derivative, negative second derivative, I found this online. It's called Mr. Smiley and Mr. Frowny Face. So if we look, Mr. Smiley's 2 eyes are positive, which means the second derivative is positive. And if the second derivative is positive, we are going to have shapes that look like either side of the smile. So the first side of the smile is concave up decreasing, and the other side of the smile is concave up increasing. But again, positive, second derivative, concave up. Positive second derivative, concave up. Mr. Smiley. Now, Mr. Frowny has double negatives as eyes, so the second derivative is negative. And similar thing here, if we break apart the frown is concave down on both sides, meaning both sides is concave down when the second derivative is negative. Sorry, I can't talk like Mr. Frowny. I actually don't know if I can frown. Nope. I can scowl, but no frown. All right, am I good to go? Hey, excuse me. So we've talked about when a function is concave up versus concave down, but we haven't talked about how we know it changes from being concave up to concave down. So again, just quickly looking back here at this graph, oh, too far. We know that the concavity changes at B and at D. But what is that called and how do we find it? So concavity changes at what is called points of inflection, or concavity changes at the point of inflection. And the point of inflection happens when the second derivative is equal to 0. So you can think of it as the points of inflection are the critical numbers of the second derivative. So to find points of inflection, we set the second derivative equal to 0, solve for x, boom. Use those points of inflections to create intervals, figure out what intervals are concave up versus concave down. So pretty much the same process as increasing and decreasing, is just with the second derivative. All right, am I good to move on? So, finding points of inflections and concavity from a graph. Now, usually identifying things on a graph is easier than solving them out algebraically. However, based on past experiences, students actually have more trouble finding points of inflection and concavity on a graph. I'm not exactly sure why, so I haven't really solved this problem yet, but I'm going to try again today. All right, so here's a graph. Boom, done. And on this graph, we want to find the points of inflection and then use those to identify the intervals of concavity. So we've actually already looked at this function before, and we've identified on this function where it's increasing versus when it is decreasing. Now we're going to be looking at it when we have concave up or concave down. All right. So let's remember that, let's see, concave up looks like this or like this. And then concave down is going to look like this or like this. Smiley face, frowny face. All right, so now if I look at this graph, I can see here that this section of the graph is a frowny face. Grr. I can also see that this part of the graph is also a frowny face. But then all of a sudden, we get a smiley face, with one side being really big. So therefore, we can see that right here at this particular point, this point is our point of inflection. And I'm going to claim that this point of inflection is at x equals negative 1/4. Now, I'm just guessing since it doesn't actually tell us. So our point of inflection is at x equals negative 1/4, which means that on our intervals of a concavity, we are going to be concave up from negative 1/4 to infinity. Then we are going to be concave down from negative infinity to negative 1/4. So basically, trying to find where a function is concave up versus concave down is trying to find out where these four shapes can be placed on the graph. And if we can find out where these four shapes are placed, then we can use them to figure out where the point of inflection is. Any questions? All right. Folks want to give it a shot? Take this graph, find the points of inflection in the interval concavity. Go. Remember, we're looking for frowns and smiles, or smiles and frowns. If anybody has an answer they'd like to share, I would be happy to hear it.
Concave up is from 0 to infinity, and concave down is negative infinity to 0.
I agree with some of that. I agree that there is a point of inflection at x equals 0, but I would argue that there are more points of inflection.
There's one at -3.
-3 or negative radical 3?
Oh yeah, radical 3. Yeah, I couldn't see it. Yeah, negative radical 3.
Yeah, sorry, this is kind of small. I would disagree that there is one at negative radical 3. I would say that there is a local max at negative radical 3. Here is what I got. And again, these are just approximations. They're not exact, so you might have something close. But that's what I got. Any questions?
Can you please go over how there's a POI at -1.5 and 1.5?
So if I pull away these kind of shaded areas, we can see that we're concave down, like we're popping out over here, and then we're popping out here. But then somewhere in this general area, it switches from being popping out or a frowny face to popping in and being like a half a smile. Whoops. And then after 0, we switch, but I think we all found that point of inflection. We switch to being kind of a popping out or a frown. And then somewhere in this general area down here, again, we come and we pop to being back inwards because we kind of have this kind of smile section right here. So because we're changing from like a frown to a smile, there's going to be some point of inflection around those points right there. I don't really know if that helped. Okay, cool. I think you're just saying thank you to be polite, but I'll take it. But yeah, I mean, this just comes at, again, I haven't cracked the secret to this because some students can just see it and some students can't. And unfortunately, I'm one of the people that I think could just see it. And I'm having problems figuring out why other folks can't. I think maybe it just comes to practice. I don't know. Sorry, I'm not going to be super helpful here. But I can just move on to the algebra part. This one's easy. All right, so now that we're all feeling very good and happy about ourselves, let's talk about finding points of inflection and concavity algebraically. Because this is pretty straightforward. It's like, oh, do this, do this, do this, do this, do this, and you're done. Good. No looking at graphs here. So we want to locate the points of inflection and identify the intervals of concavity for the function f of x is equal to 3x to the fourth minus 4x cubed minus 6x squared plus 12x plus 1. Whew. You know what, you folks, but I think that the whole world just take a day off. Just global holiday. Maybe it should be the global nap day where we just all sleep and take naps and do nothing else.
Honestly, with this pandemic, it feels like we never have a day off.
That's true. I had a day off. I took off on Labor Day. I didn't do any work that day. But that's been my last day off since March 12th. Well, actually, before that, because I didn't have a day off. What? Maybe New Year's Day. Yep, nope, I agree. Yay, pandemic. All right, so I am super happy and feel very fortunate that I do have a job. However, it was really tough back in the spring when I'm working like 20 hours a day trying to switch from being in person to being remote. And hearing about all the people who are like, oh, I'm so bored. All I can do is watch movies and collect unemployment and the $600 benefit. And it's just like, yeah, I'm glad I have a job. I'm very fortunate. But doesn't that sound great to be able to sit at home and be bored and still get a paycheck? Like, oh, that does sound great. But again, I am very fortunate to have my job. And I know that does not affect everywhere. There are a lot of people out there who, even when they got that $600 paycheck, were still struggling to get by, and we're not able just to sit at home and do nothing. So for that 4% that were able to sit at home and do nothing, I was definitely jealous. All right, anyways, back to the problem. So we are trying to find the intervals of concavity, which means we do need to find the points of inflection. And hopefully remember from 20 minutes ago that in order to find points of inflection, we need to set the second derivative equal to 0, which means we first have to find the second derivative. So f prime is going to be, let's see, 12x cubed minus 12x squared minus 12x plus 12. Isn't that fun? All right, then we just need to find the second derivative, so we'll take the derivative again. 36x squared minus 24x minus 12. Not quite as fun. All right, now we'll set the second derivative equal to 0. So 0 is equal to 36x squared minus 24x minus 12. And now we're just solving a quadratic equation. So I can see 36, 24, and 12 all have a 12 in common, so I can factor out the 12. So it'll be 12 times 3x squared minus 2x minus 1. I can then divide both sides by 12 to get rid of that guy. Boom, boom. Leaving me with 0 equals 3x squared minus 2x minus 1. Which I can factor to be x and 3, no, x and 1, 3x and 1. Negative and positive, so I might want to check that. Yep, okay, we're good. All right, so we can set each factor equal to 0, x minus 1 equals 0, 3x plus 1 equals 0, so x is going to be 1, and x is going to be negative 1/3, and these are going to be our points of inflection. So boom, solved those. Great. Now, just like the first derivative test, we're going to come in here, we're going to draw our number line, and we're going to plot our points of inflection to create intervals. And now I just need to pick test values in each of these intervals. I'll pick x equals negative 1, x equals 0, x equals 2. Now, we are looking for concavity, which means we're looking at the second derivative, which means we need to plug all these x values into the second derivative. And I'm going to use my handy-dandy calculator to do that. 36x squared minus 24x minus 12. And let's see, negative 1, 0, and 2. So we get f double prime of negative 1 is equal to 48. F double prime of 0 is going to be negative 12, and f double prime of 2 is going to be 84. So this is positive, negative, positive, which if it's positive, that's concave up. Negative is concave down, positive is concave up. Meaning we're going to be concave up on negative infinity to negative 1/3, and then 1 to infinity. We will be concave down from negative 1/3 to 1. Boom. Points of inflection and intervals of concavity.